Hi, this is lecture 14, and today I'll tell you about work, so that is integrals of vector fields, and about the fundamental theorem of calculus for line integrals. So let's do it. Let's start with a few remarks about work. So work, we defined work last time. The work that a vector field, like the one you see here in blue, does along a curve C. A curve equipped with an orientation is, so it's denoted by the integral of f dot dr over c. So that's how we defined it, right? So this integral is work. So how we define work. And the very last thing I told you last time is that we have an alternative notation for the same integral, which emphasizes the components p and q of the vector field f. And this alternative notation for the same integral is integral over c of the first component times dx plus the second component times dy. And this notation, so for example, let me give you a couple of examples. So for example, and you'll see this in the homework a lot, the integral over the curve c of y times dx, here assuming that c is a curve in 2D, a curve on the plane, is, so it's the same. So here there is no dy, so we're really integrating y times dx plus 0 times dy. So the thing in front of dy is 0, the thing in front of dx is y, so that's by definition the integral over c of the vector field with components y comma 0 times dr dot dr. So I guess one example is good enough. So so last time I gave you an explanation of why it's sensible to write to use. I mean, why this alternative notation is compatible with the first one that I introduced, but let me just give you a really quick, quick and dirty explanation of why this is a good idea, why this makes sense, and how you can remember, how you can translate back and forth between the two. So the point is that when we do the integral on the left, or when we do both integrals, in fact, we are breaking up the curve by subdividing it into a bunch of little pieces, and then dr is the infinitesimal version of these displacement vectors, right? So if I give you a displacement vector delta r, it has really two components. It's a vector, so it has in 2D it has two components, delta x and delta y, right? The difference in the x-coordinate of two consecutive points, x-coordinates of two consecutive points in the subdivision, in the partitioning of the curve. And similarly for the y components. So dr is the infinitesimal version of delta r, which has components delta x and delta y. And for this reason, it makes a lot of sense to, we can think that dr is an infinitesimal vector with components whose components are themselves infinitesimals, dx and dy, right? So f was, as I wrote before, f has components p and q. And so if we just work out this dot product, right, the dot product in the notation for the work, if we work out this dot product, we get p times dx plus q times dy, so exactly the thing I'm integrating. So that's how we can remember, how we can go from component to vector notation and back. All right, so next up, I'd like to tell you a little bit about physics. So a quick reminder of what work is all about. I have a mantra for you. So the mantra is that work is change in kinetic energy. So work is nothing but change in kinetic energy. So let's understand that. So let's look back at this picture I prepared before the beginning of the lecture. So here we have a curve with So we're doing physics. So let's consider the physical situation. We have a particle that moves along this curve in the indicated direction, with the indicated orientation. Right, it starts here and then it moves all the way to the other point along this curve. And this particle is under the influence of a force. And there I drew the vector, the force at the force vector at various points in the plane. So in this picture, you can see that most of the time, I mean, maybe I could have made an even clearer picture, but at least at the beginning, you can see that the force is mostly behind the particle, and so you expect that the speed of the particle at the end of this trajectory, or at least after a while when the particle starts going, because there's a force pushing it from behind, the particle is gaining speed. And so the speed is increasing, and the kinetic energy is basically the speed. It's a half of the mass times speed squared, so that's increasing too. And so you get some positive amount of work here, where the force is pushing the particle from behind, it turns out that there is a very nice formula for work that we all learn in high school that works for, I mean, it doesn't work in such a complicated situation, but it's just that when the force is pushing a particle from behind, so a particle is moving to the right and the force is pushing it to the right as well, and then the change in the kinetic energy, the change in a half of mv squared, is just the magnitude of the force times the distance traveled, F times d, right? So the force times the displacement. So what we're doing here in this integral situation is that we're doing basically the same thing. We're multiplying the force times an infinitesimal displacement, because our trajectory is not a straight line, but it's curved. So we work with a magnifying lens. We take the dot product, we multiply the force by the displacement, but we do a dot product because the change is going to be, so the speed is going to decrease. If the force is pointing in opposite direction with the displacement, then the particle will lose speed. So the change will have a negative sign. And for example, if the force is pointing up and the particle is moving to the right, for example, if you just get a piece of ice, a block of ice, and you let it slide, then gravity is pushing it down, but it's not affecting the block's speed, because the block's displacement, the translation is sideways. So dr is perpendicular to F, so the dot product works out to 0. So there's no change in kinetic energy. So this is a brief reminder of work, and I want to derive that. I want to now. So that's starting from something we didn't prove, that the force in the high school situation is F times displacement, force times displacement. Let me just derive the whole thing from scratch now. So let's work that out. So Y is work equal to change in kinetic energy. So let's label everything. Let's say, one moment please. So let's say that I'm just preparing my notes so I don't get lost here. So let's say that r of t is the position of the particle at time t. Right? And that f of t is the net force on the particle, so the sum of all forces acting on this particle at time t. Right? And according to Newton's second law, this is the mass of the particle times the acceleration of the particle, right? At that time, a, and the acceleration is the rate of change of the velocity, which is itself the rate of change of the position. So that's m times the second derivative of the position. So a, In principle, the acceleration could depend on time. Okay, so we have, so r of t is the position of the particle at time t, and f of t is the net force on the particle at time t. So now let's think about the kinetic energy. I'm saying that work is changing kinetic energy, so let's think about kinetic energy for a while. So the kinetic energy is 1/2 of the mass times the velocity squared by definition. That's how we define it. And but let me write this using vector notation. Write everything in terms of r. That's 1/2 of m times. Okay, so v. So v is the speed. So that's the length of the velocity vector squared. And I'm going to rewrite this once more. That's 1/2 of m times, so the length of a vector squared, I can always compute this very easily using dot products, is the dot product of the vector with itself. Okay, and I've changed my mind. I will omit the dependency on time here to make all formulas look the same. Okay, so I'm saying that work, so some sort of interval, is the change in the kinetic energy. Let's understand how the kinetic energy changes. What's the infinitesimal rate of change of the kinetic energy? And then we're gonna let's integrate. After we understand that, we will integrate that formula over time to get the macroscopic, the overall change in the kinetic energy. So let's first understand the infinitesimal rate of change of the kinetic energy. So that's dk dt. So here we're doing a derivative of a constant, so 1/2 of m times the derivative of this product. So this is the derivative of a dot product. So it turns out, if you think about this, you can do it like 1/2, so 1/2 of m times the derivative of the first one times the second one plus the first one times the derivative of the second one, right? So you should really think that r is x comma y, r prime is x prime comma y prime. So this dot product here is x prime squared plus y prime squared. So when you do the, let me not go there. Let me just encourage you to check that if you have two vectors that depend on a parameter t and you do the dot product, the derivative of the dot product is going to be given by the usual product rule. Just because the dot product of two vectors is the sum of products, and then the derivative distributes over the sum, and then you're just multiplying, just differentiating ordinary products of components, and you can use the ordinary formula to get something like this. But let me not dwell on this. And now note that the factor of 2, I can do away with the factor of 2 in the denominator, because this is equal to this, right? If I take the dot product of two vectors, that's the order doesn't matter. So here I'm adding twice the same thing and then dividing by 2. I can just take that away. So it's 1/2 of so the 1/2 goes away. I'm just left with m times r double prime times r prime. So m times acceleration times the velocity, and mass times acceleration. Well, this is starting to look good for me. That's just the force of the acting on the particle at time t times the velocity of the particle at time t. Okay, here I put the t's back in. So that's how. So this is saying that so that's the infinitesimal rate of change of the kinetic energy. Now let's see what happens when my particle, when time goes from some starting time a to some final time b. Right. So let's say that t increases from a to b. Then the change in the kinetic energy. So the change in the kinetic energy. So by the fundamental theorem of calculus, that's the interval as t increases between a and b. So the change is in the kinetic energy of the particle between these two times is the integral of the rate of change of the kinetic energy times dt. Right, so this is just the fundamental theorem of calculus. Now that's the integral for t going from a to b of dk dt. Here we computed that's the force on the particle times r prime. So it's the force on the particle, so f of t, times r prime, that's, let me just write that out in full, so that's dr dt. We'll take the t away here. And then dt, the dt that we had up here. Now we see, so now we recognize that this integral is just giving us the work. So this is a line integral over the trajectory of the curve. That's the integral over the trajectory of the curve of this force times dr. Here we can pretend that the dt cancels, and then we're left with the integral of f over dr, and that's what we defined as the work. So the work is equal to the change in kinetic energy, as I promised. So this is, I think, really cool derivation in physics that uses a lot of the calculus that we've been developing. So that's why these integrals are important. We want to know, so there's a force acting on a particle. We want to know what happened to the particle. How much faster is it moving now than it was before? So what's the change in its speed? Equivalently, what's the change in its kinetic energy? And the answer is given by these kinds of integrals. So change in energy is an important, absolutely important quantity that people want to compute in engineering and physics, and so these integrals are important too. Okay, so we're now ready. There is one final comment I'd like to make about work before shifting gears to the fundamental theorem of calculus for line integrals, which is slightly different from what we've done before. We've done here. So that's a remark about orientations, how orientations affect integrals. Okay, so let's say here I have a curve, and then I give you exactly the same curve, but with the opposite orientation. Right, so when I have this situation, the exact same, I have the same curve twice, but the second time with the opposite orientation, I'll just denote the curve with the opposite orientation minus c. And I'd like to note record here what happens. So how orientations affect the two integrals that we've learned. So the first integral that we learned, the first line integral that I taught you last time, was the line integral over the curve of a function. Let's assume we're in 2D to simplify. And the second line integral that I taught you last time, and I still discussed a little bit today, was the integral of a vector field. Okay, so the point is, there's one thing that distinguishes these two when it comes to orientations, and that is that the first integral, the integral of a function, does not care about the integral of a function does not care about the orientation of the curve, but the integral of a vector field does. So the integral of a function is over c is the same as the integral. Let me just say that the integral over minus c, in the first case, is just equal to the integral over c. But the integral over minus c of a vector field is just equal to minus the integral of the original over the original curve. Right, so the whole point, let me emphasize the signs here. So I'm just saying it happens when you change the sign, the orientation of the curve. In the first case, nothing happens to the integral. In the second, you get an extra minus sign. And this makes sense, right? So for example, let's say, so in the first case, when we were integrating, so if we integrate the function 1, the constant equal to 1 over the curve, that's going to compute the length of the curve. The length of this curve is the same as the length of the other. The orientation doesn't matter for when we're computing length, for example. But in the second case, if we're computing work, the orientation of the curve is important. If there is a force pushing a particle from behind, the kinetic energy of the speed of the particle is increasing. But so the change in the kinetic energy, that is the work, is positive. But if a force is pushing a particle is against the trajectory, so if a force is pushing, instead of pushing the particle from behind, it's like blocking the particle, then the kinetic energy of the particle will decrease because of that, and so the change will be negative. So if I say that the particle went from here to here or from there to here, and the force stays the same, the effect in the kinetic energy will change by a sign. All right, so let's move on to a shiny new subject. I'd like to tell you now about what happens when you integrate a derivative. So this is the fundamental theorem of calculus. Fundamental theorem of calculus for line integrals. Okay, this is the first and last time I will write fundamental theorem of calculus in full. From now on, it'll just be FTC. So FTC for line integrals. So here's what the theorem says. So theorem, I'll just give you the formula. So it tells us what happens when we integrate the gradient of a function over a curve, right? The gradient of a function, I should remind you, is, so recall, let me put this note down here. So recall, the gradient of a function is in 2D this vector field with components whose components are the x partial and the y partial of the function. Right, that's in 2D. In 3D, so in 3D, it's going to be, it's going to have 3 components. Okay, I'm getting lazy. Let me start introducing the shortcuts. So this is f sub x, this is f sub y. In 3D, we have 3 partials, and we just put all of those in our vector. Okay, so if we integrate this vector field over a curve C, what we get is, well, it's easy if you know what the function in the curve is. So let's say this is our curve C. Let's say the starting point is A and the end point is B. Well then, according to the fundamental theorem of calculus for line integrals, the integral of the gradient of a function over this curve with respect to dr, because the gradient is a vector field, is just equal to the value of the function at the end point minus the value of the function at the starting point. So that's it. So I don't have to set it up, I don't have to parameterize it, I only need to check what are the starting point and end points. End point of the curve, I need to, think a little bit about how much, you calculate f at the 2 endpoints, and there you go, I computed my integral. So that's really cool. So this is like, so if I know a vector field is the gradient of a function, I can always exploit this theorem to compute integrals really easily. It's not true that every vector field is the gradient of a function. We'll see that in a moment, but when we do know that, then this theorem is our best friend. Let me hide this for a second because it's taking. Let me just keep the notation, the 2D case here. I don't want this reminder distracting us from what I'm going to discuss here on the side. So what I'd like to do next, before I show you all the implications or start discussing the implications of this theorem, I'd like to show you why it is true. So I want to, so this thing so at the heart of this theorem is the usual, the standard, the old familiar fundamental theorem of calculus you guys learned in single variable calculus. So I want to show you how this is really a repackaging of that theorem, how we can deduce this theorem from that one. So let's do that. So proof. Moment, please. Okay, so I will write everything in 2D for simplicity. So we're doing the integral of the gradient of f dot dr. So writing everything out in 2D, this is the integral over the curve C, and then the gradient is f sub x comma f sub y, and then dr. So I'm going to assume that I already have a parameterization of this curve. I can always find a parameterization of the curve. So maybe it's hard to find, but there always exists one in principle. So I'm going to take one of those and then write dr in terms of that. So I'm going to expand my integral. So replace my line integral by an ordinary integral with respect to a parameter that when t is little a, I'm over here. So this is r little a, this is r of b, and here in the middle I have r of t for some intermediate value of t between a and b. Okay, so now what I did here was set up the line integral using some parameterization that I know exists, but I don't know I don't need to know how to find in. So for what I'm doing, any parameterization will do, and I know that there will always exist one. So now let's work out this integral. Let me work out this dot product. That's the integral for t going from a to b of the x partial times dx dt plus the y partial of f times dy dt. We integrate that with respect to dt. Okay, now we squint at the thing inside the parentheses and we think, I've seen that before, right? So this is, if you think about it, this is the rate of change of the function of f with respect to t, right, by the chain rule. I'll even give myself some room to indicate that now I'll use the chain rule. Right, so we've seen this before. This x partial times dx dt plus y partial times dy dt, that's the rate of change, that's the change of f, that's ddt of f when I express x and y in terms of this parameter t. And then you integrate that with respect, I'm integrating that with respect to dt. Now, by the usual FTC, now I'll use I'm integrating a derivative, so I can use the usual FTC, fundamental theorem of calculus. This is just the value, so I just, I just evaluate the f, the primitive, at the two endpoints. So I just get f of x of b comma y of b minus f at x of a comma y of a. And this is exactly what I promised before, right? Because as I noted on the left, x of the input of f in the first occurrence of f is b, and the input of the second is a. And so this completes our proof, because we proved that the integral of this gradient is just the difference of those two values. So this is really cool. This theorem is really cool, but in a sense is expected. If you integrate the derivative of a function, so here we have a function that depends on several variables. The derivative is really a vector. You get a vector of derivative. So the derivative of this function is going to be a vector field, and I'm saying if I integrate, so I defined the integral of a vector field, and with that definition, the integral of this vector field just recovers the values of the original function. Okay. So this theorem has many, many amazing implications. I'd like to begin exploring one of them with you. So here's the implication. So if let's say I had a different curve, maybe more complicated. So here I drew in blue another curve, C prime. Right? So do you see that the integral over C, so do you see that the integral over C, so the integral of the gradient of any function, right? If I take if I integrate the gradient of a function f over C, the answer is the same as the integral over C prime, right? Because the integral in both cases is f of b minus f of a, right? Assuming that C and C prime have the same endpoints. So you see that if I'm integrating the gradient of a function, the integral doesn't depend on the curve over which I'm integrating, it only depends on the endpoints of the curve. So, so this is a special property of a vector field. So so not every vector field has this property. So now let's think about what it means to have this property. So let's say that f is a vector field. Right, so either in 2D or in 3D. Okay, maybe I should write it like this, or all the stuff. Let's say I have a vector field, then the following three properties are equivalent. So we have three equivalent properties. Properties. Oh, fit. Good. So three equivalent properties. So property number one is that the integral of f dot dr is path independent. So this means, path independent. This means if two curves have the same endpoints, then the integral is the same. Okay, so we've seen that gradient vector fields have this property, right? By the fundamental theorem of calculus, if two curves have the same endpoints, and if the vector field f is the gradient of a function, then the integral over both curves of this gradient is just difference of the values of the function at the two endpoints. So in particular, it's the same. You get the same answer for both line integrals. Okay, so that's a property a vector field can have. Here's another property. The property is the vector field is conservative. So f is conservative, and this word is borrowed from physics. It has basically the same meaning as in physics, slightly generalized, because in physics we only talk about conservative forces, whereas in this class we are talking about, we're saying what it means for an arbitrary vector field to be conservative. So conservative means that if I have a closed loop, then the integral of my vector field over that loop is always going to be 0. It's going to be 0. So property number 2, so here in number 2 we're talking about vector fields such that if I give you a closed loop and I compute the work of that vector field around the closed loop, I'm always going to get 0. Right, so for example, gravity has this property. Gravity is a conservative force. If you have a child that's it's swinging in it's swinging on a swing, sitting on a swing and moving around back and forth. So if you say you look at the motion, you just track the motion of the child from the bottommost position to the highest possible point and then back, right? So the child starts really fast until it stops and then starts coming back and comes back really fast. So you see that let's ignore friction in this example. So in this situation, so if there is no friction, the velocity of the particle will start maybe at v, will go to 0, and then when it comes back, the velocity will be minus v, right? But the speed, if there is no friction, the length of v minus v is the same, so the speed won't change. And if you look at this trajectory, just this closed trajectory, which goes, and then comes back to the same starting point, the work done, the change in the kinetic energy, that is the work done by the gravity, is 0, because the speed didn't change, and so the kinetic energy didn't change either. So gravity is a conservative force. Gravity has the second property over here. So the third property that a vector field can have is that it's an example. It's covered by the fundamental theorem of calculus. So a vector could be a gradient vector field. So not every vector field has this property, but some have. So F, here's the third property. F is a gradient field. So in other words, there exists a function f of xy, or in 3D would be f of xyz, such that the gradient of that function is my vector field, right? So this is not automatic. So in 1D, this was automatic. If I give you a function like x squared, it is the derivative of another function, namely x cubed over 3 in that example. And even for an arbitrary continuous function, or even piecewise continuous function, you can always find another function whose derivative is my given function. But it's not always true. So not every vector field is the gradient of a function, right? That's a special property. And number 3 is looking at those vector fields. So the statement of this, so here we have a proposition, I guess, that these 3 things, 1, 2, and 3 are the same. So if a vector field has one of these properties, maybe the property number 1, then it also has properties 2 and 3. So when I say these are equivalent properties, I'm saying that if one of them is true for a vector field, the other 2 are true. And if one of them is false, the other true or false. They're either true or false simultaneously for any given vector field. I won't prove all of them here, but let me just show you how we can derive one from the other. So here's why this is true. So first of all, property 3 implies properties 1 and 2. That's the easy, now that we have the fundamental theorem of calculus, that's the easy implication. So this is true by the fundamental theorem of calculus, by FTC for line integrals. Right, so for example, let's say you have 3. We look at 3. So let's say we have property 3, that our vector field is the gradient of some function. Then we look at the integral. Let's look at property 2, say. Let's look at property 2. So we have a closed loop. So for a closed loop, the starting point is the same as the end point. And so when I evaluate the integral over here, I'm going to get the function little f at the starting point minus function little f at the end point, rather the other way around. But in any case, I'm going to look at the difference of values of f at the same point, and so it's going to be 0, right? The value of the function is determined by the point. And so that difference is 0, and so you get 0. And similarly, so number 1 we discussed before, that if I have two curves with the same endpoints, the integral over gradient over those two curves is for both curves is going to be f at the endpoint minus f at the starting point, at the common endpoint and common starting point. And so the two integrals are the same. So the equivalence between 1 and 2 is a fun exercise, is a fun thing to think about. I'll give you a picture that will help you, that you can use to think about this. So if I have two curves, let's say I have two curves. I have 2 points here, and a curve C1, so C, and another curve C prime. Okay, and they have the same starting points, same endpoint and the same starting point, same endpoints. God. Okay. So I'll even move this to the next page so I can write a formula to convince you. So we're concerned. So now let's look at something. Let's consider the difference of the integral of. So let's say we have any vector field, and we look at the integral over C. And then how is that different from the integral over C prime of that same vector field? So if I do this, that's the same as doing the integral over C minus C prime of f dot dr. Right? So the effect so this minus sign, I can bring it down. I can replace this with a plus sign by putting a minus in front of C prime over here. By our earlier discussion of orientations, and then when I add two integrals, that's the integrals over two curves. That's the same as doing just one integral over the union of both curves. But now C minus C prime is this curve that goes from here to here and then comes back right along minus. So it goes along C and comes back along minus C prime back to A. So this is a loop. Right? If I have two curves with the same endpoints, the difference, and I'm going to go back and undo a change that I made here. So the point is that if I have two curves with the same endpoints, the difference of the value of the integrals of the vector field over the two curves is the same as the integral of that same as the integral of that same vector field over the difference of the curves, which is a loop. Right? And now you see that if I know that integrals over loops are 0, then this difference is 0, and so the two are the same. Or if I know that this difference is 0, that is because the integrals over curves with the same endpoints are the same. So if I know this difference is 0, then the integral over the loop will be 0 as well. So that's how you can relate 1 and 2. If you know that property is 1 is true, then property 2 is true as well, and vice versa. So I won't explain why 1 implies 3. That's the harder implication. I won't do it now. So I won't explain if you know that the integral of the vector field doesn't depend on the path, only depends on the endpoints. How can you find a function f whose gradient is my vector field? I won't tell you how to do this now, but I'll do it next lecture. So, soon. Okay, to close today's lecture, I'd like to discuss the question of when is the vector. So when can we use the fundamental theorem of calculus? When are these three properties true? So which vector fields are conservative? Let's look at this, starting from an example. So for example, how about this one? So f, let's say f is the vector field y comma x. So is this the gradient of a function? Can you think of a function whose gradient is y comma x, whose x partial is y and whose y partial is x? So maybe you want to pause the video and think about this for a sec. Okay, so I'll be back in 3, 2, 1. So the answer is yes. For this function, for this vector field, you can't. So this is a gradient vector field. It, is a gradient field. Right. So f is the gradient. So I'm sorry. If let me call little f. So if little f is the product of x and y, x times y, then the gradient of little f is just y comma x, and that's our vector field. That's the given vector field f. So this guy is a gradient field, but some vector fields are not gradient fields. So here's an example that is not. So f, if I just put a minus sign in there, so that's minus y comma x is not a gradient vector field. And here's how I know. This is going to look like black magic, something really mysterious. Here's how I know. If I call the first component P and the second component Q, right? So here's how I know this is not a gradient vector field. Call the first one P and the second one Q, and then I take the x partial of the second component. Right? If I compute that, I'm going to get 1. On the other hand, if I compute the y partial of the first component, so in this case, P sub y is negative 1, I get another number. I get negative 1. Okay, so now we observe that the two are different, and so for this reason, that's how I know that f is not a gradient field. This looks really, really mysterious, but it's true. I mean, but it's a test that we can always make to check whether a vector field is a gradient field. So in this case, it's different. But in the original case, right, if I do q sub x, if I take the x partial of the second component, I get 1, and if I do the y partial of the first component, I get 1 as well. So both it's the same number, and that's consistent with the fact that I was able to find a function whose gradient was my vector field. But in the second example, no matter how hard you try, you can never find this function f. So let me quickly explain why this criterion works, and we'll call it a day today. No, you know what? Let's do this with more time next time. So I think this is a good time to break today's lecture. So thank you for listening, and I'll see you guys on Friday. Bye-bye.